So we're going to be discussing Boolean algebra today. Now we have been talking about digital circuits for a couple of weeks now. We're just going to continue talking about digital circuits. There's really a lot to unpack in chapter 7, and I think it's important to understand, well, really all of it. So you'll notice last time we talked about Carnot maps. Here we're going to talk about Boolean algebra and then kind of bring all of these concepts that we've talked about together. I just went super unfocused on the video, which is great. So the idea behind Boolean algebra is we can do mathematical operations on logic statements. Okay. Oh, my camera's struggling to focus today.
Yeah, some of the videos just had
I was gonna say, Skylar, did you take my camera last night? Woo! Go for another round. Yeah. Yep. Someone's struggling today. All right, so we can do mathematical operations on logic statements. All right. Now, basically what that does is our goal here is we want to be able to represent a circuit as a series of mathematical statements. Okay, so we can do math on logic statements, and then we want to represent a circuit as math. So this is the foundations of what Boolean logic is. Okay, so we need to go over some definitions first. Multiplication represents an AND. All right, now we can get away with this because in a Boolean statement, you only have zeros and ones. So here, A, B, C, D is only 1 if A equals B equals C equals D equals 1, meaning they're all on. That's what makes it an AND statement. What?
The video is just like solidly out of focus.
The lighting in this room sucks today for some reason.
As you walk out of the frame.
Yeah, apparently I'm just gonna have to keep doing that. Well, whatever. So, if we write something as A times B times C times D, we are writing it as A and B and C and D. Okay? Addition. This represents OR. So, here, A plus B plus C plus D is 1 if A, B, C, or D is 1. Basically, if they're all 1, you get like 4, but it's only represented as 1. So you end up with, is this not 0 or is this 0? Okay, this one's a little bit harder to grasp, ironically, because here, this kind of makes sense. If any of these is 0, all of them are 0. But here, if you have more than 1, it's still just 1. Because it's just checking to see whether or not there's a voltage present. Okay? Does this make sense? Okay. If you put a hat on the number, it represents not. All right, so as an example, this is only true if A is 0. Maybe you have a sad definition of a hat.
Not even fit for the head of an A.
It's more like a halo, it really is. Oh well.
Yeah, I can hear the angels now.
Yeah. So yes, now we will be representing all hats as halos.
Now that's going to be a loop that falls over A and sinks to the bottom.
Actually, this kind of looks like a ring toss, where like the end result of this is, I won!
I can't drink, you never win.
You never win, my friend. I only win. All I do is win, no matter what.
Point to Mario, just turn it down.
No, this is the hat. So here, this is true if A is equal to 0, but we can also take this and do some fun things with it. This is true if AB is equal to 0.
Whoa, it's dark.
This is true if A plus B is equal to 0. So the not statement, there's a lot of things that we can do with it. We can also go and say, this is true if A naught B naught is equal to 0. Yep, it is that convoluted. Look at how many hats those guys are wearing. Look at how fun that is. That's a real party. It's like a Zane approved party right there. Would have been funnier if Zane was still here. But.
Everything is under the line is has to be 0.
So here, having a line, this here goes over a function. This here, that's just over a letter, it just represents a component. Okay? So here, if I were to write this out, A, B, if A goes into a NOT gate, and then they go into an AND gate like this, this would be represented as this is A, this is a NOT. So Q here is equal to A naught B. Okay? But I could also turn this into A and a B, have this go into a NOT statement, have this come into this and then turn this into a NAND, and then what this would be Q is equal to A naught B naught. Okay? Have I confused you yet?
No.
Yeah.
One, like there was A is true if A equals 0. One is 1. When is A equal to 1?
When A is equal to 1, then it's 0. So this is only telling you the true statements, but then it's false if A is equal to 1. And here, this is false if AB is equal to 1. This is false if A plus B is equal to 1. Okay? So I just wrote one of the conditions.
Oh, it's just one. Okay, okay.
Yeah.
That's right.
Okay, let's take this and take some circuits and write math equations from them. Ivana. This light burned out. That's why it's so dark.
Now you are dark.
I'm an engineer, yeah, and I know how to fix lights, but that doesn't mean I want to pay for it. Also, facilities tends to get mad at me when I fix stuff on my own. I mean, you'd think so, but not everybody fixes things right, except for me. A naught, B naught.
Okay, I thought the B had one.
Nope. Okay. So we'll do an example here. And our example will be, we will have A, B, C, and D. What we'll have is we'll have an OR statement. We'll have an AND statement. We'll have a NOR statement. And then, I don't know, we'll have an XOR statement. That'll be fun. And then we'll finish all that off with an AND gate. Okay? So here, this will just be B and A. Oh, shoot. I'm gonna need to move this over a little bit. A, B, C, D. So we'll have B and A go into here. C and D will just pass through. Okay. We'll have all four of them go into here, because why not? Sounds like fun. And then we'll have B and D go into here. Okay, then we'll take this, plug it into here with this, and do that. Okay? So, now that we've written out all of our logic gates, what do? Well, here, this is C1, this is C2, this is C3, this is C4, and that's Q. All right? Now what we can do is we can take each of these and write them as their logic statements. So what is C1 equal to? Well, what is C1? You're right, but hold up. What kind of gate is C1 attached to? It is an OR gate, okay? How do we represent an OR gate? Yes. How do we do it in Boolean algebra?
Plus.
It's a plus. Okay, and what are the two inputs to this OR gate?
B and B.
A and B. So here, C1 is equal to A plus B. And all of you thought we couldn't make addition confusing.
This just giving me calculus 2 flashbacks.
Except we're not doing calculus. We're doing like addition and multiplication.
C1 and C2.
That's it? C1 and C2, yeah. We got to.
Okay, so we're going to write the statement for C2. What kind of gate is C2 coming out of? It's an AND gate. What all goes into C2? Well, the AND gate connected to C2. All of them. How do we represent AND? Multiplication. A times B times C times D. Okay. All right. Now let's do C3. What kind of a gate is C3 connected to? It is an OR. Okay, give me like 5 minutes. I'm gonna throw up a problem. I'll solve it at the beginning of the next video, and you guys can run to Joel's class. Okay. So this is a NOR gate. What are the inputs to this NOR gate? D and B. So what we have is this is the regular OR gate. This is the NOR gate. Okay, we didn't talk about XOR, so I'm just going to do this one for you. C4 is equal to C1 with a circle X, C2. And then the last one is Q is equal to, well, what kind of gate is Q attached to? It's an AND. What inputs go into Q? Okay? So how do we represent a NAND? C3, C4 with a hat on top. Yeah.
Could you go and plug in parentheses C3 and 4?
Yes. And in fact, this is what we would do to write the full equation. We've got all of these written out. So this is equal to C1 x C2 times D plus B with a hat on top. And then we take the knot of all of that. And this one is equal to A plus B. So I guess I'm going to have a double parentheses. Cross A, B, C, D. Times D plus B, knot, and then throw it in a knot. So just writing it out. Okay, now I'm going to give you an example problem, which I guess you guys can see at the beginning of the next video. So just watch the last video that I'm posting, and you guys can run to Joel's class. But that's what we'll be doing then. I would pause it and try to solve it yourselves.
Would you be required to know all of the simplified version too?
All right, so let's do an example. I'm going to give you 4 inputs. I want you to figure out what Q is. So here, A, B, put them closer together. A, B, C, D. Oh yeah. Yeah, except I didn't break into your house. Oh yeah! It smashed through your wall.
Never seen Boolean Algebra. Serious? I don't watch TV.
Bro.
Not when you were 10? No.
All right. So I got your 4 gates, C1 to C3, C1, C2, C3, C4, and Q. So I guess that's 5 gates. I want you to solve for what Q is.